Welcome back. We are still discussing beds, the molecules as springs or springs as molecules if you like. Don't let this nice glass distract you. The thing is that it's time that by the end of this presentation you'll make a choice which one you think is better suited to describe a physical picture. And arguments like this one is more comfortable don't really hold in this case. So just a reminder, we are talking about soft molecules like springs, and we said that we can describe the molecule like a spring. So this is the potential, which is associated with the spring, the square of the coordinates. And then if we add an electron, we have this blue potential. And indeed, like if it's similar to springs, that when the spring is free without anything attached to it, then it has a certain resting point. When we attach a mass, it has a different resting point. You see this is different in the coordinates. And indeed, if they vibrate around a different position, and it looks somewhat different. So, and then we said that the best way to visualize charge transfer between two such molecules is to consider the system as made of two molecules. The one that contains the charge, in this case, is A, and the one that's going to receive the charge. And the two of them form what we call reactants and products, following the notions used in chemistry. And we said that in this picture we can visualize the attempt frequency. So the molecule is bringing the charge to a position where it can transfer, but it takes several attempts until the probability takes over and it moves to the other side. Of course, everything's symmetric, so it can move back later on. And this transfer rate, we said it's composed of the attempt frequency, which is somehow associated with the phonons in the system. It's not so trivial to find out which type of phonons are associated with the transport, but usually in practice what we'll do, we'll say that this is a normalization frequency. It is somewhere around the phonons, but which phonons it's really difficult to precisely determine. We have the energy that is required to bring the two molecules to this conformation where the charge can attempt to move without any change of energy during the process. And then, of course, there is this overlap between the wave function of the two molecules, because at the end there is a tunneling process to happen between the two molecules, and it has this certain probability. And as we said, if the probability is relatively low, then we would expect the attempt frequency to be larger, or there will be more attempts until we manage to get to the other side. So far we have discussed two identical molecules, the A and B and the E naught, as we said previously. But really the system we are interested in is not this one, because we have a charge that is hopping in a disordered, if you like, material. And the easiest or the simplest way to describe the disorder in the picture we have discussed so far is that the background energy, E naught, is changing between positions. And that could be due to different packing and other effects that we are ignoring. That's usually the case. When you add something not fully justified, it's because there is an effect we have ignored. So really, how would we add this effect of sites not being equal? And it could be, as we saw before, due to disorder. but this could also happen due to electric field. If we apply a bias that falls between these two sides, then one of them will shift down, and what we'll still be interested in is in finding the rate for this charge to move from one side or even against the slope backwards. And really this is what we'd be interested in, and what we have to do is to replace this symmetric picture with the idea that when the charge is on one molecule, the total energy is lower than when it is on the other. So we are really going to break this perfect symmetry, and you can imagine that by breaking the symmetry means that we say that when the charge is on the right molecule, in this case, the total energy is lower by delta G0. And you see, this is what we did. We shifted it down. And really what we'd be interested in is to know what is the energy that is required to hop in this direction. And of course, we'll also be interested in hopping in the other direction, although in some cases we'll say that hopping back is so improbable that this will be governing what's going on. But at the end of the day, we can't ignore the back reaction, because things are going to be at a quasi-equilibrium in most cases that we'll be interested in, and definitely in this course. So really, just as we did before, we want to know the rate. We have the attempt frequency that we had before. We have the P that we have said it exists, and we are mainly interested in this delta G. So how do we calculate this delta G as a function of delta G0? So really what we have is we know how to describe these two potentials, and they are parabolic. One of them is centered around the coordinates of the reactants. The other one is centered around the coordinates of the products. And we've shifted it by delta G0, which could be either positive or negative depending on your point of view. And really to find this delta G1, we have to first find the crossing point in terms of the coordinates, and that, when we plug it back into the potentials, will tell us what energy was required. So that's really simple. Just as before, we plug it in, we get this equation, and now we need to use this QC to extract the energy. So basically what we have to do now is just a simple algebraic procedure that I won't take you through it. I'll just talk a little bit longer, so you'll have time to read it yourself. You can practice reading while ignoring background noise in this case, if you like. And really there is not much logic to manipulating it to reach the final expression that I'm reaching. And I'm doing all these manipulations simply to bring it to an expression that I know I'll want to use later on, or I know that in the literature most people like to see it presented in that way. So really, after we've reached this point, we know these relations that we found before between the binding energy, the activation energy, etc. And we can arrive at this expression for the energy that needs to be invested. And I've placed the delta G naught in absolute terms and said it's for going down in energy, just to be sure, because sometimes it is confusing what means up, what means down, and this is the case. So really, once we have this energy that need to be invested, we have everything that we need. And now we really need to write the hopping rate for this kind of reaction, if you like. And we know that just as before, we are going to write it in a very similar manner. We'll just replace the activation energy that we had before with this one. and we know the full expression for it. And it's interesting to see that now the expression is composed of several terms. We have at first something that looks like before. The binding energy is still existing here as a pre-exponent, if you like. And then you see all this effect of disorder or external electric field goes into the second expression. So really we still have the effect of simply the material being soft, and then the idea that there are differences in space between the position of the sites. Just as a short break, I think I forgot to mention that often we use the word polaron to describe the motion of the charge, or the charge with the motion. And really the polaron really had a direct meaning in the past when it was introduced in the context of inorganic materials. And the idea there was that once you put a charge somewhere, it would naturally polarize its environment. And this polarization alters the environment, and hence it affects the motion of the charge. In our cases, we've seen the materials are soft, so polarization also means structural distortion, and really it's the structural distortion that is governing what's happening more than the polarization or the electronic polarization itself. So really when we say polaron, we mean that it's the charge plus the distortion, because we can't really separate between the two when we are discussing soft materials. And we say that we can't separate between the two. Of course, that always has some assumption behind it. And one of the things you may want to ask yourself is what might be the maximum speed at which this distortion can still follow the charge around. So we've discussed quite a bit the idea of the material being soft. We introduced the notion of a polaron. We've seen that the motion of a charge in these materials is dependent on the existence of the phonons. We have this kind of binding energy that really makes it difficult for the charge to get the necessary energy to make the jump, and this energy is really invested in the molecule itself. And we have this full expression that describes how the rate would change when the sites are varying with energy, and you can think of this as the initial state, and this is the final state. And this way we'll see how it being affected. Actually, I would like to check if what I said as a definition of the final or initial is correct in terms of the absolute value that you will get here. Sometimes I'm wrong. So why is it called self-trapping, the polaron binding energy? And the similarity to traps, as you may imagine, is first of all we have this energy that we need to activate to get out of the trap. And also we see here that there is probably going to be some kind of electric field dependent of the rate, which would then be translated to the mobility, because as we've discussed, the relative height or the relative energy difference between two sites is really dependent on the electric field that exists between the two positions. So this is really something that is often very difficult to distinguish between the issue of polaron, distortion, or the issue of traps or disorder. But there are places, or there are instances or scenarios where we could really distinguish between the two, not always, but it's possible. And for that, we have to ask ourselves, what have we learned regarding to traps that we wouldn't expect it to exist in this case of self-trapping. And we can go back to the first issue of defining traps, how we distinguish between different types of traps. And really, we have seen that if the traps are not too deep, or like if you like, the disorder is not too high, then if we raise the charge density enough, then we should expect to see the field dependence and the activation energy disappear, because we'll reach the trap field limit. There is also another thing that we want to discuss, which is a little bit more advanced, and for that I brought this reference here, and it's if we are looking into thermoelectric properties, and the experiments are not so simple doing that, but it's becoming more popular these days, then traps would add an activation energy to the thermoelectric parameters, while the polaron would not. So far we have invested some time and energy in developing an expression for the hopping rate, and that is hopping rate for soft molecules, but not all materials are soft. Amorphous silicon also has this odor, and it's not considered to be so soft. So is it really the only hopping rate that is acceptable? And if you have some experience, then you know that definitely not. There is another one which is much more popular, that is called the Miller-Abrams rate. So what is really the general form for hopping in a system? And usually when things look really complicated and difficult to track, we have a very powerful tool in our hand that in most cases is really useful, or it's true. And we say that funny things could happen in the structure, things could go strange, but really if we zoom in on the scale of two molecules, then we can apply what is called the detail balance, or in some cases we say there is a local equilibrium, and then we translate it to the idea that between two single molecules, effectively there is no current, or if you like, the current that is being drawn through the system is negligible compared to the current that's being exchanged between the molecules. So really this is what it means. We have an expression which says that the current that for going from the I site to the J site, which is the probability for the I site being occupied, the J site being empty, and this is the hopping rate from I to J, that we would be interested to know what it should look like. And this is the hopping backwards. And under a local equilibrium, they must be almost equal. This is very similar to the discussion we had about equilibrium in the context of contacts, if you remember. So really we want to find a general expression for this R. And you see F is the Fermi-Dirac statistic plays a major role here. So we remind ourselves what it is, and this is the quasi-Fermi energy that exists in the material. And now we plug one into the other, and we found that hopping in one direction divided by the hopping in the backward directions must be related for this Boltzmann expression. So if you demand the rate forward and backward to be activated for this expression, it really says something. It really contains some kind of a requirement that you demand that the system will obey. And you can guess that or understand that from the way I've reached this expression. So really, we need to fulfill this requirement, and you can check if the expression we arrived at before fulfills it. I hope it does. But really, the simplest way to fulfill it is really, if we are going up in energy, we have to pay the penalty of this energy difference. All of it is being paid only in the upward direction. And if we are going down, if we don't pay anything, the probability is 1. Of course, all this can be preceded by some kind of a prefactor that it doesn't have to be constant. It can be constant, but it can also be proportional to the absolute value between going right or left. So really, when we divide the two, then this will really be eliminated, and we'll be left with this basic expression. And this simplest form, as I said, this could be a constant that is not dependent on the energies, and we can arrive at what is called the Miller-Abrahams rate, where we have the phonon, or the normalization frequency. We have the tunneling rate between two molecules, which is what we call the P. And then we have this Boltzmann requirement to make sure everything works well. And before we proceed, I have to make some type of comment. In 2000, when we decided to go deeply into these hopping rates, we really read carefully this paper that everyone cites, and got extremely frustrated. You can't really find this expression in this paper that everyone cites again and again and again, which looks really strange. Luckily, nowadays with the internet, you can really get hold of Abraham's thesis. So we got the thesis, very excited, opened the thesis. This expression doesn't exist there either. It took a while until I realized that there is a book by Shklovsky that contains this expression, and he says that it's by Miller-Abrahams, and he cites this paper. So probably they had some kind of discussions, who knows. But it's strange that no one really notices that you cite something that helps no one. It's just strange, but it happens. So really what we have seen so far, we have seen the polaronic rate and the Miller-Abrahams rate. I just wanted to bring an illustration to show that the differences are not just minor differences. And what I plot here is the probability to jump as a function of the difference between the two sides. And you see the Miller-Abrahams has this step-like function. So if you go up, you pay. If you go down, you don't pay. But here, you see that for the polaronic rate, or the Miller-Abrahams, or the Marcus theory, when it holds, then there is a maximum, a certain maximum at a lower energy. But if you go too low, the probability goes down again. So really that has some implications on some dependence of the rate as a function of electric field, disorder, etc. But these are not so simple to discover, so that's why a lot of the papers that you'll encounter still use the Miller-Abrahams, which is much simpler. And our group are among the sinners that in most cases really use this Miller-Abrahams. We have good excuses, but it's not relevant. So really, we have managed to find the hopping rate, and you can choose the one that you most like, either the one that has the Marcus theory built into it, or if you like, what people call the Miller-Abraham's rate. And now what we want to do is to use that in order to find the current. So we're going to go from 2 molecules to many to see how the charge is going to flow across the film. And our hope is that we'll be able to use all this description to really extract what a d and mu would be. Because at the end of the day, if we are going to simulate devices or to learn how devices work, we need to use d and mu. There's almost no way around it, because if you try and apply ab initio calculations to every time you want to understand a device, you will never understand anything. So really, we have to somehow simplify things, and most popular way of doing that, or the most useful way, is to try and somehow describe all the complexities in terms of d and mu. And really, that's what's going to happen. We are going to find the current, how it flows, and see how it being translated into something useful. So as I said, we are interested in finding d and mu, but before we do that, we have to ask ourselves, is it legit to describe what we think of as current using d and mu? Can we simply, as we did before, find the drift current, divide by the electric field, and define mu? What about d? And really, it seems that d and mu has some meaning behind it. First of all, you need to understand that d and mu are statistical quantities. And for something to be well defined, the statistics has to be well defined. So really, there has to be a large number of states that the charge is moving across. And not that only, we need that the electron would be sampling enough, because what is the meaning of statistics of 5 sites? And this is really sounds like silly, but it has deep implications on the noise that you may find in some of the papers. And really, d and mu are designed or intended to be macroscopic quantities. And for them to be macroscopic quantities, it means that things has to be varying relatively slowly. If things will be varying very quickly, then the statistics is not going to be applied for the entire device, and the whole idea of using d and mu becomes non-legitimate. So of course, this model or this expression is always true, but you have to use it under the right physical scenarios. And we'll extend a little bit about it in the next presentation. If you like just a bit of intuition, if you go and attend a race, let's say like in these terrains where there are lots of pitfalls and hills, and you go to the person who is broadcasting it and you ask him, at which speed did the cars arrive? I bet you that his first answer would be, what do you mean by the speed at which the cars arrive? Just think about it. So for the behind the scene, we'll add a few things that we generally don't talk about during the lectures, but they might still be interesting to know. So one of the things we discussed but didn't really pay much attention to it is this P, which I mentioned. It's an overlap integral. It contains some kind of tunneling, but really I thought that we should add a bit more to it, and what P means is that we have the M2 molecules, which has come to a configuration which is the best there is for the charge to transfer, but then there is still this space between the molecules, that the charge has to pass. If you like, you can look at it from a different perspective, where we plot the energies relative to the vacuum level. And really the charge has to move from one molecule to the other. And basically what happens is, since there is this empty space in between, there is tunneling. So really this is what P actually is supposed to mean. And this picture is rather confusing sometimes, because it looks as if there is nothing here to pass, so why do we need this P? And the reason is behind the fact that the configuration coordinates do not really contain all the information we need. And if you like, in this context, we might have preferred to go and display it this way. And if we make it look like this way, it becomes more intuitive that there should be tunneling. But this is not something that is typical, so it's only here in the behind the scene slides. So if we talked about the configuration coordinates, then this is really confusing, these coordinates. And I thought I'll bring some perspective which is not directly relevant, but has some meaning to it nevertheless. So let's just put this aside. And I thought I'd take the opportunity and introduce to you Israel as a national trail. If you like, the map of Israel is going to be our coordinates. And it's interesting to know that this unique trail is one of the best 20 as voted by the National Geographic. So we could use these links to learn more about it. But this should by no mean that I am recommending that you will go out of the lab and get some sunshine. If you decide to go out and have a life, that's at your own risk. So really this is the map, and you see the trail here, and this is really the recommended path. So you will go through the state of Israel from north to south, or from south to north, and see lots of interesting things that you might find in these links. But this map doesn't really look at all like configuration coordinates, because first of all, it doesn't have the same layout. So really, if I try to illustrate what the configuration coordinates sometimes mean, is if we just walk along the trail and we plot the height as we go along. So this, for example, could be height as a function of distance, and we have linearized the map, if you like, in a certain way. And of course, it has a lot of important information if you are the one who's going to walk the trail. But really, it doesn't have all the information you would need. And of course, when you do some simplification, things go missing. And really, the other things, one of the things that is missing, for example, if you look at this map only, and I ask you if you are going across the state of Israel from south to north, or vice versa, what are the chances that you will go through Jerusalem? It's impossible to answer using this map, because there are so many different ways to cross Israel, and there are so many different ways to go through Jerusalem, that this map definitely cannot answer it. And this is one of the things that is related to reaction rates, if you like. You can find a bit in this paper that I liked, but it's also in textbooks.